Imagine a place where time itself grinds to a halt. A place where the ticking of the clock becomes meaningless, and the concept of past, present, and future blurs into one. A place where the very fabric of space-time is stretched to its breaking point. Here, the laws of physics as we know them are pushed to their limits, creating a realm that defies our understanding. This is the realm of black holes, the most enigmatic and awe-inspiring objects in the cosmos. These cosmic giants hold secrets that have puzzled scientists for decades and continue to be a source of fascination and wonder. These celestial monsters are born from the death throes of massive stars, collapsing under their own gravity until they vanish from sight, leaving behind only an invisible gravitational pull. The process is both violent and beautiful, a testament to the incredible forces at play in our universe. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their clutches. They are the ultimate traps, where the escape velocity exceeds the speed of light, rendering them invisible to the naked eye. They are cosmic abysses, shrouded in darkness and mystery. The very idea of a black hole challenges our perceptions of reality, making us question the nature of existence itself. But perhaps the most intriguing aspect of black holes is their profound effect on time itself. As we venture closer to these cosmic giants, we enter a realm where time behaves in ways that are completely alien to our everyday experience. As we approach a black hole, time begins to slow down. This phenomenon, known as time dilation, means that an observer far from the black hole would see events near the black hole happening in slow motion. This is not a trick of perception, but a fundamental consequence of Einstein's theory of general relativity. According to this theory, massive objects like black holes warp the fabric of space-time, creating a gravitational well that affects the flow of time. Gravity, you see, is not just a force, but a warp in the fabric of space-time. This warping effect is what causes time to slow down near massive objects, and nowhere is this effect more pronounced than near a black hole. And the stronger the gravity, the more pronounced the warp, and the slower time flows. In the vicinity of a black hole, time can slow to a crawl, creating a region where time, as we know it, stands still. Black holes represent the ultimate triumph of gravity over matter and energy. They are formed when massive stars, many times the size of our sun, exhaust their nuclear fuel and can no longer support themselves against their own immense gravitational pull. As the star collapses, its core implodes, creating a region of infinite density and zero volume known as a singularity. Surrounding the singularity is the event horizon, the point of no return. Once something crosses the event horizon, it is forever trapped within the black hole's gravitational grip. Not even light, the fastest thing in the universe, can escape from beyond this boundary. The event horizon is defined by a distance from the singularity called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who first calculated it in 1916. Imagine for a moment that you were to approach a black hole. These cosmic giants, remnants of massive stars, are among the most mysterious and powerful objects in the universe. Their gravitational pull is so strong that not even light can escape once it crosses a certain boundary known as the event horizon. As you drew closer, you would feel the inexorable pull of its gravity, stretching your body like spaghetti in a process known as spaghettification. This phenomenon occurs because the gravitational force at your feet would be significantly stronger than at your head, causing your body to elongate and eventually tear apart. But even more strange, you would witness time itself slowing down. This is due to the intense gravitational field of the black hole, which warps space-time around it. The closer you get to the event horizon, the more pronounced this effect becomes. From your perspective, time would seem to flow normally. You would continue to experience seconds, minutes, and hours just as you always have. However, the reality outside your immediate vicinity would be drastically different. But to an outside observer, watching you from a safe distance, your movements would appear to slow down, eventually coming to a standstill as you reach the event horizon. This is because the light from your actions would take longer and longer to reach the observer, making it seem as though you were moving in slow motion. You would be frozen in time, forever poised on the brink of oblivion. The event horizon marks the point of no return, where the gravitational pull becomes so strong that escape is impossible. Any attempt to move away would be futile, as the forces at play are beyond comprehension. Escaping from a black hole, once you've crossed the event horizon, is a feat that would defy the laws of physics as we know them. The escape velocity required would exceed the speed of light, a barrier that, according to our current understanding, cannot be broken. To break free from the clutches of a black hole, you would need to achieve an escape velocity greater than the speed of light. This means accelerating to a speed that is, by all accounts, impossible for any object with mass. And as Einstein's theory of special relativity tells us, nothing can travel faster than light. This fundamental limit of the universe ensures that once something crosses the event horizon, it is lost to the black hole forever. The price of escape is simply too high, a reminder of the immense power and mystery that black holes hold. Section 4. A Tale of Two Twins, Time Travel's One-Way Ticket. To truly grasp the mind-bending nature of time dilation near a black hole, let's consider a thought experiment known as the twin paradox. This paradox is a fascinating illustration of the effects of relativity, particularly how time can stretch and compress depending on one's velocity and gravitational field. Imagine two twins, Alice and Bob. They are identical in every way, sharing the same genetic makeup and having lived the same number of years up until this point. Their bond is unbreakable, and they have always been inseparable. Bob remains on Earth, living his life as usual, while Alice embarks on a daring space voyage to a nearby black hole. This journey is not just any ordinary space trip, it is a mission to explore the most extreme environment in the universe. Alice's spaceship is equipped with a powerful engine that allows her to hover just outside the event horizon, resisting the black hole's pull. The event horizon is the point beyond which nothing, not even light, can escape the black hole's gravitational grip. Hovering here, Alice is in a region where the effects of time dilation are most pronounced. After what seems like a short while to Alice, she returns to Earth. She is eager to reunite with her twin brother Bob and share the incredible experiences of her journey. However, she is in for a shocking surprise. But to her astonishment, she finds that Bob has aged significantly more than she has. While Alice feels like only a few years have passed, Bob has lived through decades. His hair is gray, his face lined with the marks of time, and his body shows the wear of many more years. This discrepancy in aging arises because time flows differently for Alice and Bob. The closer one is to a massive gravitational source like a black hole, the slower time moves relative to someone farther away. This is a direct consequence of Einstein's theory of general relativity. While Alice is in close proximity to the black hole, time slows down for her relative to Bob on Earth. This means that for every moment Alice experiences, Bob experiences many more. The intense gravitational field of the black hole warps the fabric of space-time, causing this dramatic difference in the passage of time. So, while Alice experiences only a few years of time passing, decades or even centuries could have elapsed for Bob back on Earth. This thought experiment vividly illustrates the strange and non-intuitive nature of time in our universe, showing us that time is not an absolute but a relative experience, deeply influenced by speed and gravity. Section 5. Beyond the event horizon, can anything escape a black hole? For a long time it was thought that nothing, not even light, could escape the gravitational pull of a black hole once it crossed the event horizon. However, in the 1970s, physicist Stephen Hawking proposed a revolutionary idea. Black holes might not be completely black after all. Hawking showed that, due to quantum mechanical effects near the event horizon, black holes could actually emit a faint thermal radiation, now known as Hawking radiation. This radiation arises from the creation and annihilation of virtual particle pairs near the event horizon. Occasionally, one particle of the pair will fall into the black hole while the other escapes into space, carrying away a tiny amount of the black hole's energy. Over vast stretches of time, this process could eventually lead to the complete evaporation of the black hole.